Hey everybody, this is Alex Merced, and I'm making this video to kind of go over the data engineering landscape. The goal of this video will be to one kind of understand sort of what does a data engineer go through and the data landscape and all the terms here. So even though I'm going to be focusing on data engineering, whether it's the data analyst or data scientist, you should have a better appreciation for the data landscape as a whole at the end of this video. Okay, so bottom line is when we think about the data landscape, the idea is this: businesses, organizations, governments, they have systems that do things. And when they do things, they generate data. So whether it's like a startup that's adding new users, so you have to have a somewhere you have to store that new user, or maybe someone put in an order and you got to store that order, or you added a new product and you got to store that product. Data is being generated. Or it could be sort of data that represents things that have happened. Okay, so maybe every time a user clicks on a page, you may want to track that event and you may want to track that data real time and you stream that data. Okay, so oftentimes the data that an organization is generating is going to fall into three buckets. Okay, first is the data that gets stored in your databases. So again, think users, products, orders, and these databases that you store them in, they store them in a way that's called transactional. Okay, the idea is that the way the data is being accessed is generally one at a time. I'm adding one user. Okay, I'm retrieving one user to get their data. Okay, I'm handling one order at a time. You're generally adding a thing, deleting a thing, updating a thing, but you're generally doing it one row at a time. Okay, so in these databases, they're referred to as OLTP systems, which means online transactional processing. The key word there is transactional processing. You're processing transactions, generally meaning one thing at a time. Okay, so it makes sense that you grab the data as a row because I'm working with that one user, with that one order, so I want all the data for that one thing. Okay, and they're optimized for that type of manipulation of the data to do that to those types of workloads really, really fast. Now, oftentimes when we're capturing events, like we want to capture what users are doing on a page, we're capturing, things that a device are doing, any kind of data that's just kind of like you want to capture real time. Oftentimes, you don't store it in the database right away. What you do is you use something like a Kafka to broadcast that message. Okay, so Kafka becomes sort of like this broker, okay, of things that have happened. Okay, and generally those all those little events that have occurred get categorized into what's called a topic. So in Kafka, there's lots of topics. So there might be a topic for clicks. There might be a topic for other types of events that may have occurred, and you're streaming that data in. So basically, my website, every time a user clicks on something, I may end up sending that data into Kafka, and now there's this topic in Kafka that has all those different events that then other systems can then pull from. Okay, and they can do that real time. That's why it's called streaming, because you're not capturing the data little by little or processing it little by little. It's all happening as it happens, and it's available everywhere as it happens. So you have streams, and then you have other data that you might collect. So for example, companies might decide that they want all their emails to be analyzed, or IoT devices, so any device that has some sort of like online functionality, so your smart this and your smart that is generating information, and so forth and so forth. So you have all these different places that data is being generated and saved. But none of those things at the point that you're using them are really optimized for analytics. They're optimized for the transactions, for the using of the thing that the business or organization is doing. But in order to grow the business, we need insights. We need to kind of understand, like, hey, what people are doing with our product? What do people are not doing with our product? So we can make decisions on how to evolve that product. Or if you're a government, make decisions on how to best allocate resources for different policies. Before that, you need to do analytics. And that generally comes in the form of sort of three different buckets. Okay, there's visualizations, where you try to visualize and analyze the data. Okay, this typically can be in the form of a BI dashboard, where you have some separate tool like Tableau or Power BI that shows you the chart or the visualization. Okay, you could have data apps where you build on a full-on application for exploring the data. But generally, this is going to be more the realm of the data analyst. Their job is to kind of take data to help understand what's happened in the past. So I'm going to take that data and try to create the visualizations, the applications, basically take that data and create a consumable version to be able to take a look at the past to make decisions about tomorrow. Okay, but sometimes it'd be nice to just have those decisions made for you, aka have predictions made. And this is the realm of AI and ML, where you can create machine learning algorithms that can take in data and predict, or just automatically programmatically make decisions. Okay, say, hey, this is the right decision to make, or this is how things are, this is what the weather's going to be tomorrow based on the weather we've seen in the past. Okay, essentially be able to sort of more programmatically do things. And then you go to the next level where you have AI, where it can go beyond just like predictions. It can go into actually making suggestions, coming up with ideas, creating whole new things. Of course, the concept of generative AI. This is going to be the realm of data scientists, but they're going to need all that data too to build these AI and ML models. And then another profit center for a lot of businesses is taking the data they generate and selling it to other people, data sharing and marketplaces. Okay, where basically you might be a weather company, or you might be the Weather Channel, and you have all these meteorology tools that are gathering all this weather data, and wouldn't it be nice to be able to sell that to make some extra money to people who want to build weather functionality into their apps or build other systems that may need that data. So, but this data, again, is not being used for transactional workloads, like one thing at a time. They're being made to these ends. Okay, so they need to be in a completely different setup. They need to be set up in systems that are optimized for analytics, which are known as OLAP, online analytical processing. Okay, so the way the data is actually physically stored in these systems is different. The way the data accesses these systems are different, so that way they're faster for those types of workloads. But the data doesn't just magically get from point A to point B, and this is where the data engineer comes in. Okay, the data engineer fills in this whole gap in the middle to figure out, how do I take the data from all these systems and then move them into other systems for all these things to happen, and do it in a way that's fast enough for the needs of the company, that's easy enough to access with quality data. Okay, because at the end of the day, it's like, if it's too hard for the data analysts and data scientists to access the data, they're not going to use it. If it's not the correct data, they're not going to get good insights and have good models. If the data isn't in the right format, isn't optimized, it's going to be slow, and it's going to take a long time, also being a problem. So there's all these different things that the data engineers, they're basically trying to figure out how to package it efficiently for all these analytics use cases. So typically what happens, okay, you have two types of data. You have structured data, which is, again, the data that kind of sits in databases. So this is data that typically is, you have, like a list of users, a list of orders. So every user has a first name and a last name and an email. You have certain things. So think about data you would put in like an Excel spreadsheet. That's structured data, okay? Any data that would fit into an Excel sheet or a Google Sheets table, Airtable, that's structured data. Now, data that doesn't fit into that very nicely, things like emails, videos, photos, that's unstructured data. Okay, you can't just, create a table out of a picture, or at least not in an intuitive way. So typically you need to store that data somewhere that can hold structured and unstructured data. So typically what happens is that the first step in the journey is that you have some sort of storage. Okay, and this is referred to as somewhere to store all that data, and that's referred to as the data lake. Okay, so all the data from these systems are going to get stored in that data lake. And again, literally just think of it as like a giant hard drive. That's really all it is. It's a giant hard drive where you're storing all this data as files, in the same way you store files on your laptop. But the idea is that all the data is now in one place for you to do whatever you need to do next. Okay. Now, again, this is not like a database, so it doesn't have the same type of, like a database usually allows you to ask it questions. Okay, I can just sit there and say, hey, take the sales table and get me all sales above $50. And I can express that in a language called SQL, seek structured query language, and it would get me that data. Data lakes don't do that. Data lakes are they're just a bunch of files stored in storage, though you can use tools to run queries against data lakes. I'll talk about that a little bit later on. So some of that data you're going to want to have stored in a system like that you could use SQL against. Okay, and this is where a data warehouse comes in. So you would take some of that data and move it into a data warehouse. Okay. And then that data then becomes available for all these different types of workflows. And again, this data also, and then for some things, like for like unstructured data. So if you're building like an AI model that works on photos, you're not going to have those photos in the data warehouse, so you might build that directly off the data lake where all those photos are stored. Okay, so essentially everyone's accessing the data either from the data warehouse or the data lake. Okay, and once in a while they may never move the data at all, and the data may just still be in their database in not necessarily the most optimized format, because again, databases are optimized for transactional, not analytics. So that's all well and good. Okay, so that's fundamentally like what the data engineer is doing. They're figuring out, okay, how do I, what is the code, what is the thing I need to do to take the data out of these systems, aka export. Okay, do I need to change the data at all? Transform, the T, and then load this data into these systems. So that's called ETL. So I'm going to write code or use tools to ETL the data, take the data out, change it if I need to change it, transform it, and then save it in the data lake, and then take some of that data and then ETL it again into data warehouse. Now there's a cost to that, because nowadays we generally use cloud tools. Okay, so that means I need to get a virtual computer from your favorite cloud vendor to run this code. That's compute. Okay, and that's going to every second that computer is running costs you money. I need to store the data files somewhere. Okay, that data's got to be physically stored somewhere. So that's storage. That's going to cost you money. Okay, generally there's this big network within the cloud provider. And as long as the data is moving within the cloud provider's stuff, that's fine. But the minute it moves outside of the cloud provider's network, they charge you for that. That's called an egress fee. So oftentimes when I might land let's say I'm using AWS, Amazon Web Services, S3 would act as my data lake. Okay, so if I move that data, if I land all this data into S3 as different files, CSV files, JSON files, MP3 files, Parquet files, all those different types of files, I may want to move some of that data into the data warehouse to work in tables. Okay, but I might be using some sort of data warehouse tool. Think of like something like a Snowflake that might have its own sort of cloud that might not be within the same network as mine. So as soon as that data moves out of it and I do that ETL, I'm hitting that additional cost of egress. So you can see like the more you have to move the data, the more it costs money, because you're paying for the compute, you're paying for the storage, and you're paying any network or egress fees. Now, the data has to be modeled. Okay, so essentially across the movement of this data, sometimes it happens in the data lake, sometimes it happens in the data warehouse, but typically that data has to go from just being the data in these systems to being the data that data analysts need. So generally you go through three sort of steps, okay? And people call these different steps all sorts of different things, okay? So generally the first step is that you just land the data somewhere, okay? So that's typically you're just gonna land that data in the data lake. And this is referred to as your raw or bronze layer, okay? There's other names, but raw or bronze are probably the most typical. And the idea here is it's just the data unchanged. It's just the raw data, okay? I've taken it out of these systems, I've stored them somewhere without doing anything else to them, okay? Now the problem is there might be duplicates in that data, so I might have two copies of the same order in the data or the two copies of the same user when I really only want one. There might be incorrect data. There might be all sorts of stuff. So in that case, what I want to do is I'm going to take that data, write some code to take that data, clean out the duplicates, do all the stuff that needs to make it nice and, fill in the empty spots, fix the incorrect records, do all that. And that is going to be called we'll call it the prepared layer or my silver layer, okay? There's different ways you can call it. Again, the point is the 3 steps. Okay, whatever we call the 3 steps doesn't matter as much as that there's generally 3 steps. And this is the clean data. General use. Now, what does that mean? I've cleaned up the data, but they're big data sets that capture big chunks of the data. So in this case, a sales table that has like every sale ever, an orders table that has every order ever. You know, and generally, the questions they're asking isn't on every single order that ever existed. Okay, they're not asking. The questions are going to be more like, hey, what are my average sales this month? Okay, what are my, what is the average sale per user or something like this. So there's more like specific ways you want to store the data to answer very specific questions. So once again, I'm going to take, now that I have the data, now that I have a clean copy of the data, I can now take that data and chop out and make little small copies of small subsets of the data that answer specific business questions, that use specific business terminology, that basically makes sense to those analysts and those data scientists who understand the business, but they're not dealing with all this stuff in the middle. So we're basically taking all this raw data and turning it into something that they understand in the context of the business. Okay, so this is where, like, outside of the technology, it's important for the data engineer to spend time developing things like ontologies. So when you ever hear that term like ontology and knowledge bases and things like that, it's all about just making sure that everyone in the business is using the same language to refer to things. So that way, when we create the technological data, you know what it means because we're using terms that everyone kind of knows what they mean. Because every business might be using the same words different ways. So part of the data curation process is also curation of that sort of unified way of referring things, that ontology of how we refer to stuff. Okay, and so this last layer, okay, can be in this is called the gold or semantic layer. Okay, and that's different than like a semantic layer product. Okay, I'll explain what I mean by that. But the idea is that these include business logic. The idea is that I took that orders table and turned it into maybe the orders for June 2024. Now I have a small table that is orders of June 2024. Okay, or average orders by user. Okay, that might be another table I create out of that. I'm creating data sets that answer very specific types of business questions based on the kind of questions that are being asked in the business, which requires me to go talk to those analysts and talk to those scientists and kind of understand what are they trying to figure out, because how am I supposed to design all of this if I don't understand the business the way they understand it? So a lot of being a good data engineer is, and actually honestly the harder part, is those communications and understanding and getting that context around the business and building those shared meanings, okay, which are not things that are usually technologically solved. Cool. Okay, so I have these 3 layers. So the idea is that generally, like, my workloads as a data engineer are going to fall sort of 3 categories. I'm either landing that raw data somewhere, I'm cleaning that data, or generating all the little mini data sets that'll be used for a specific dashboard or for a specific AI ML model, or be shared on a data sharing platform like on Snowflake or AWS. Now, where does this physically happen? Am I doing it on the Data.Lake? Am I doing it on the data warehouse? That differs by company. So some companies may do all of this on the Data.Lake. Okay, some companies will just take the raw data, land it in their data warehouse, and do all the modeling, all this in the data warehouse. So where this physically happens can differ. Okay, so we are now down to here. But again, when you think of semantic layer, the term semantic just means sort of like things that have meaning or meaning. So the idea is that, like, a sales table doesn't necessarily have much meaning, but like sales of, if I'm thinking of like Amazon sale data, like sales of electronics for June 2024, that has a much more specific business meaning. So the idea is like this is your layer of things that are much more specific to the business. So a semantic layer is somewhere where you help organize those data sets. So essentially you're organizing your was where you identify and kind of the central, there's two ways you can do a semantic layer. Essentially, often originally semantic layers were built in the BI tool, like a Tableau or a Power BI. The problem is multiple teams might be using different BI tools to access the data. So the problem is, what if we both need to define electronic sales for June, and now the team that uses Power BI defines it in their software, and then the team that uses Tableau defines it in their software, which is referred to as an extract. And now you have two copies of the same data that might be slightly defined differently, which is going to lead to different results. So this is where you start getting into semantic layer solutions like Dremio, like Cube, like at scale, that try to say, hey, instead of defining it in your BI tool, add a layer before your BI tools where you can define these things. Okay. Granted, Dremio does a lot more than just a semantic layer, but give this central layer where you can define these things, so that way when Power BI connects to your semantic layer and Tableau connects to your semantic layer, both teams are going to use the same definition of the same that same semantic data set. Okay, so that's sort of like the purpose of the semantic layer and some products that deliver a semantic layer. Then there's things like virtualization. So right now we're assuming that I'm literally making a physical copy of the data. So I copied the raw copy of the data. I then made another copy of the data with everything cleaned. And then I made a bunch of small copies of different subsets of the data for different use cases. Okay, the problem with more and more copies is that, one, the cost of doing all those jobs, all that code I have to write and all the storage, okay, and the complexity of all that, and making sure that all those copies are consistent and none of them have inconsistent data, which would be really bad. So the idea behind the concept of virtualization is basically doing that without making a copy. So the idea is and typically when you think of a data virtualization system, essentially what a data virtualization system is a system that allows you to connect different data sources, okay, and be able to run queries directly on all those sources from one place. So what a data virtualization tool would be, so we'll say here, what would happen there is you would connect all your databases data lake, data warehouse, and now I can see all those tools, all that data, even though I haven't moved any of it, it's right where it is, I can see it all in one place. Okay, so that's data virtualization, just something that allows me to see all my data from one place and then possibly run queries against it. And then when I'm running queries across multiple sets of data, that's referred to as a federated query. I'm basically taking pieces of that query, running them in different systems, but coming up with one result. Okay, so that's a federated query, typically a thing that data virtualization systems do. Okay, they can connect the different types of data wherever you have it, and then run queries against that data where you have it. Sometimes what they also allow you to do is virtual modeling. So essentially I can model that silver and gold layer virtually through what's called a view. A view is essentially like a SQL definition of the end result, not a physical copy of the end result. Okay, so basically I'll define all the changes to the data as SQL, and now what's going to happen is that every time I check out that view, it's running that SQL to give me the end result that I wanted. Okay, but I'm still querying that original raw data set. So the cleanup is being done every time, but I'm not having that extra physical copy, which can be fine. Okay, again, there's always a trade-off, right? Because if basically what happens, if I'm using a view, I'm running that compute to calculate those changes every time, but I don't have to store the end result because I'm not copying it. Okay, so pro and con when you virtualize a data set is that no copy, but two, you're running more compute because you're recalculating the result every time you use that data set. Okay, so the question is, are those computations so expensive that they outweigh the cost of storage? In that case, and these are the kind of trade-offs you have to kind of make a decision about. A lot of times storage is much cheaper. okay? Especially when you get to bigger and bigger data sets. Cool. So data virtualization system, again, allows me to see all my data sets, allows me to run queries against all my data sets. We can help break up things that are referred to as data silos, where basically, I may have access to the data warehouse, but there's data that's not in the data warehouse. So basically some data I need is over here in the database still and never been moved. And now I have a problem. So then the data analyst has to go ask the data engineer, who then has to figure this whole thing out. With a data virtualization platform, that data analyst can just grab the data they need from where they need it. This is one of the things that platforms like Dremio can do. Okay. Then there is virtualization. Then there's the concept of data mesh. Now, data mesh is less of a technological thing more than a paradigm. The problem is, like, there's more and more data, right? So usually what happens is you'd have a central data engineering team that does all of this. The problem is, like, if you're at Amazon and you have like many different business units, like the electronics department, it's gonna be very different than the books department and very different than the appliance department. They're all gonna have different terminology, different contexts, different, it gets really, really complicated. So the idea with sort of in a pure data mesh type approach is that you take the division of labor. So how do you split up that work? Instead of a central team, one big central team that touches everything, you have smaller teams that do subsections referred to as domains. Okay, so basically you break up the business into a variety of domains, different parts of the business. So again, that could be electronics, that could be, thinking of Amazon, appliances, books, etc., clothing. And you basically say, okay, hey, you're in charge of curating what's called a data product. So taking doing that raw silver gold, creating the data sets, doing that data modeling that is needed for that subsection of the business, and delivering that end result that is used by the data analysts. Okay, so basically you're going to deliver that end data product, essentially that gold layer or a packaging of it at the end, and each team is responsible for their product. The benefit of this is it creates like a more clear set of accountability. Like it's the team doing the electronics data product that's responsible for problems with the electronics data product. Okay, well, when you have a centralized team, you say I have a problem, but you don't know who did your last request, and you don't, they're all one big team, so you don't really know. There's not like a who's responsible for the problem with that particular data set. It's just like you make a request and you wait till it gets fulfilled, which works pretty well to a point. But you do get so big as a company or an organization that becomes very difficult. So in data mesh, you break up the business into different domains. You set up a team that creates a data product for each of those domains, and then you try to create that shared meaning. So again, this is where like the concept of computational governance, you try to create a shared understanding of how that data is going to be delivered and governed at the end, so that way it still feels unified even though it's done separately. So that's data mesh. Okay, and we're getting pretty close to the end. A couple other now these other terms are just going to be quick terms I just want to kind of touch on. As I mentioned, governance. So oftentimes when you're talking about governing data, there's two ways you can govern data. There's RBAC, role-based access controls, where basically you're saying what people can do with the data. So like people can read the data, people can write the data, people can update the data. So you're able to specify what they can do, not by just saying, hey, they have access to the data set or don't have access to the data set, but you're able to specify the different roles of actions they can take with the data. Then there's FGAC, or fine-grained access control, where you're actually specifying what parts of the data they have access to. Do they have access to these particular rows of data? Do they have access to these particular columns of data? And traditionally, this is something that's been done at the engine level, meaning the tool that actually does the computation. The problem with that is that the world is moving more towards, because the problem is most tools that do computation usually would come with their own storage. So you'd have to move that same data into different storage for each tool, okay? And that gets really expensive and really complicated really quick. So what people are wanting to do is move towards a lakehouse architecture where their data is accessible by all tools. And the way you do that is that instead of having your data in lots of different places, and lots of different data styles. So while data virtualization solves a portion that problem one way, data lakehouse solves it a different way by saying, hey, let's take your data storage system, your data lake, and just say make that the universal landing place for your data, and you put it in some sort of, and you're going to organize that data into different data sets using something referred to as a table format, okay, like an Apache Iceberg, okay? And really all Apache Iceberg is just providing you is data about the data, metadata. And that data allows engines to look at, let's say, 1,000 different files as if it were one thing, one data set. That's all it does. Okay, but now that I can do that, you can now treat your data lake as a data warehouse. So all the benefits of being able to run SQL against a data warehouse now become possible on the data lake at the same scale as a data warehouse with the same kind of performance as a data warehouse. So this becomes what's referred to as, so when you add a table format, then you turn it into a data lakehouse, because now you can treat it like a data warehouse. You don't necessarily need the additional data warehouse. You can now just use your data lake as your data warehouse, which reduces the amount of data movement you need, and so forth. So basically the world is moving towards trying to do a lot of these types of governance. Instead of having to govern the data in different tools, because you have 5 different tools that you use, and now you have to govern the data and create all these governance rules across different tools, they're trying to say, okay, hey, is there a way we can do this across all the tools? And a lot of this conversation is becoming part of what's called a lakehouse catalog. Okay, so when you think of catalogs, there's oftentimes 2 different types of catalogs that are talked about in this space. They're what's usually referred to as enterprise metadata catalogs. These are more places, it's more like a phone book for your data for your employees. The idea is that your employees may not know what data is available to even ask for access to the data. So something like an Elation, a Colibra, they're used to be as like a phone book for your data. They allow you to list all your data everywhere and list information about that data and give someone where your users can then request access for that data. That's different than what I'm talking about here. I'm referring to what's called a lakehouse catalog, which is more of a tool that is going to basically be aware of all the different tables you have on your data lakehouse, so that way other tools know which tables you have, okay? And the idea is that since this tool is aware of these tables, why can't this tool also keep track of your governance rules? And this is sort of like the cutting edge of the industry right now, figuring this piece out, okay? Because if I can move governance to the catalog, then if I'm using Dremio, if I'm using Apache Spark, or I'm using whatever tool, then the governance is the same, and I don't have to worry about, just because this team wants to use this tool, that they're going to be maybe less secure than because all my governance rules are an X tool. Okay, and that's a lot of what's going on right now. How do you facilitate and make the data work across teams when different teams want to use different tools? So hopefully this all has made the data engineering world more clear to you, the viewer of the video. And thank you all very much. Again, always subscribe to the channel, and I'll talk to you all later. Have a great day and enjoy.